Are you able to see my screen?
Yes, we are. You can start.
Good morning, everyone. My teammate Rutuja and myself, Nathan. Today, we are here to present understanding and takeaways from the paper ViViT, a video vision transformer. The presentation is divided into following logical parts. In introduction, we'll be talking about some background, the motivation, and the problem statement that the authors are trying to solve. In related work, we'll be talking about a couple of similar problems solved for different architectures, but we'll just be giving an overview and some important things. In embeddings, we'll be talking about different methods for embedding video clips. Authors have developed multiple variants, playing with the spatial and temporal dimensions of the input video, and thus they have created 4 models, which will be discussed in this section. And they have also performed in-depth ablation study comparing with major state-of-the-art models. In the end, we'll conclude the presentation with some of our insights and further future work. First, we'll look into what transformers really are. Transformers were initially just used in NLP, but what we saw in vision transformers, which was covered in previous presentations, that they are now challenging CNNs, which have been the backbone of vision-related problems since many years. The main fundamental difference between these two is the local versus global context. We know that the CNNs only look for dependencies in and around the pixel window, which focuses on the local context, whereas the transformers have the bigger picture because of pre-tokenization embeddings, which focus on the global context. And therefore, transformer understand the complete picture quickly and perform better. Now, when we consider the case of videos, the implementation is a little bit complicated. Before that, let us look into what spatial and temporal dependencies are. When we are trying to segment an image and trying to find how a pixel is related to its neighbor or other pixels in the image, these are known as spatial dependencies. And in some applications, like in activity recognition, for which we have to process multiple frames because there are dependencies on the time axis as well. These are known as temporal dependencies. On the right side, we can see the transformer architecture. We can see that here it is the same transformer encoder was used as it was used in vision transformer, and also the same position and token embedding system. The only difference is tokenizing more than one frame in one go, and also let the transformer learn the spatial and temporal dependencies. The first thought that comes to everyone's mind is to give the entire video as input, and let the transformer learn, which is actually the first model proposed by the authors. But the issue here is the number of tokens. Because attention mechanism requires computation between each pair of tokens, this is a very serious issue, specifically in videos, as we already need to process more tokens for any video task. We'll see later how these problems were resolved by the authors. A couple of related work which were used in the understanding of this paper are Attention is All You Need, which talks about how a transformer, a model architecture, entirely relying on the attention mechanism can be used to draw global dependencies. The transformers allowed for significantly more parallelization and were better than the go-to CNS model in problem like sequence modeling. And the second paper, which is an images worth 16 cross 16 words, which was covered in previous presentations, it talks about how the transformers were further extended to be used for image-related problems like image classification. Now we move on to the embedding video clips, the author considered two simple methods for mapping a video to a sequence of tokens, and then add the positional embedding and then give the input to the transformer. These two methods are uniform frame sampling and tubelet embedding. Now we'll discuss them in detail in the upcoming slides. So first is the uniform frame sampling. It is a very straightforward and simple method for tokenizing the input video clip. First, we uniformly sample frames from the input clip. Then we embed each 2D frame independently using the same method as vision transformer. And then we concatenate all these tokens together, as we can see here in the image. From common sense, we can say that this process is simply constructing a very large 2D image to be tokenized following ViViT, that is vision transformer. And the second type of embedding is the tubelet embedding, which is a bit complex than uniform frame sampling. In tubelet embedding, we start with extracting non-overlapping spatiotemporal tubes from the input video clips and then linearly projected. This method is simply an extension of vision transformers embedded into 3D and also corresponds to 3D convolution. We can see that this method fuses the spatiotemporal information during tokenization itself, whereas in case of uniform frame sampling, only spatial information is fused during tokenization, and temporal information from different frame is fused later by the transformer. Now, next we will look into the 4 models proposed by the authors, which will be explained by Rutuja.
Hello everyone. Sorry. So the first model that we will be looking into is the spatiotemporal attention model. In this model, it basically takes tokens from all the frames and passes through the encoder, just like the vision transformer, that is the ViViT. Now, in this case, in this model, in contrast to the CNN, each transformer layer models all pairwise interactions between the spatiotemporal tokens, which means is since the first token of first image can interact with the last token of last image, this results in like really long range interactions across the videos from the first layer. And this leads to a drawback of giving us a quadratic complexity, which can be seen in the slide. This drawback of complexity was then overcome in the second model, which was proposed by the author. The second model that the authors proposed was the factorized encoder. Now, in this model, just as the name suggests, they factorize the encoder, which means that all the frames are passed through spatial encoder, as we can see in the figure. That is, every single frame is passed through separate spatial encoder. And then the output features which we get are then passed through the temporal encoder. This basically facilitates the late fusion of temporal information as first spatial information is obtained, and then it is used into getting temporal information. In this model, there are more parameters since 2 encoders are involved instead of 1, which is the spatial and the temporal encoder separately. But there are a few floating point operations as everything is not interacting with everything directly, which was the case in model 1. So the tokens do interact with each other at long range as well, but they do that indirectly. So the model 2 overcame the complexity issue of model 1, and the complexity of this model is much less as compared to the first model. The third model that the authors proposed was factorized self-attention. Now in this model, they just used one encoder. But as we can see from the figure, inside one encoder, they use like two self-attention blocks. One is the spatial self-attention block, and the second one is the temporal self-attention block. This model has same number of transformer layers as model 1, since there is just one encoder as it was in model 1, but its complexity is same as model 2 since everything again is not interacting with everything directly. So how does this work? So first, every block calculates the spatial self-attention among all the tokens extracted among all the tokens extracted from the same temporal index, and then the temporal self-attention among all the tokens extracted from the same spatial index. So in simple words, what it does is it takes the input tokens, it reshapes it as number of frames into spatial dimension. Then it performs this spatial attention, and then it reshapes it appropriately so that it can be input into the temporal self-attention block, which we see in the figure. And then it performs temporal self-attention, and the output of which is then passed on to the next transformer block. So overall, they also experimented again with the order of the self-attention blocks as to which should come first. The spatial self-attention block should come first, or the temporal self-attention block should come first. And through experiments, they found that it doesn't really matter. So yeah, this is all about model 3. The final models that the authors proposed is the Factorized Dot Product attention model, which is basically the best of all worlds model. This model has the same computational complexity as model 2 and 3, while it retains the same number of parameters as the unfactorized model 1. This model is a bit complex in the sense that first we get all the attention heads and divide them into two parts. In this case, the concept of neighborhood is very important in the sense that for half of the heads, we compute a dot product over only spatial axis, as you can see in the right half part of the figure. And for the other half, over only the temporal axis. We then generate keys for these attention heads. And the main idea here is to modify the keys and values for each query to attend over the tokens from the spatial and temporal index. Then for the divided half of the attention heads, we attend over the tokens from the spatial dimension by calculating the bias, which would be the attention for the spatial dimension, and the rest we attend over the temporal dimension by computing ViViT, which is for temporal dimension. And finally, we combine the outputs of multiple heads by concatenating them and using the linear projection. So these were the 4 models that the authors have proposed. Now next we see how initialization can be done by leveraging pre-trained models. Now we know that ViViT has shown to only be effective when trained on like large-scale data sets. But the largest video data sets such as kinetics have several orders of magnitude data that is less labeled. So because of that, training large models from scratch to high accuracy was extremely challenging. So to overcome this issue and enable more efficient training, the authors basically initialized the video models using pre-trained image models. With this, 3 problems arised. The first problem that they faced was of positional embedding, which is that the video model has NT times more token as compared to the image model. And they overcame this using by initializing the positional embedding by repeating them temporally, so that all the tokens with the same spatial index have the same embedding. So throughout the frames for every spatial token having the same spatial index, it will have this same embedding basically. And the second problem that came with this approach was basically with model 3, because this model has 2 self-attention blocks instead of 1 inside the encoder. And the solution that they proposed for this was to initialize the MSA module with a pre-trained module of it. And secondly, they initialized all the weights of temporal MSAs with 0. The third and the most important problem that they faced is embedding weights, because all the ViViT models are pre-trained using images and hence have 2D filters. But since in this case, we are using tubulate embedding, as we saw in the previous slides, it requires 3D filter. So there are two solutions to this. The first one is inflating filters, and the second one is central frame initialization. Inflating filter means at every layer, we will take weights corresponding to every image. And we will replicate it t times, where t is the number of frames. And as we can see from the equation, we just divide all by t. So it is basically just like averaging based on location. The second method which they adopted, in which they kept image weights at central frame and initialized everything to 0. So basically, these are the three problems they faced and the solutions that they came up with. We have so far seen like 2 embeddings and 4 variants of the models. And using this, the authors performed various experiments and got various results, which we will see next. So before that, we will see what experimental setup they used to perform these experiments. So for this, they used the ViViT-based architecture, having a tubulate size of 16x16x2. And the models were trained using synchronous SGD and cosine learning rate. And pre-training is performed with ImageNet and JFT dataset. Next is the Ablation Study. So in the Ablation Study, we compare the input encoding methods, which is the uniform versus the tubulate embedding, and see which performs best. And we see of the 4 model variants, which some of them are factorized and unfactorized models, which one performs best. So in terms of encoding, for this experiment, the authors used ViViT-based architecture with a spatial temporal attention model on the Kinetics 400 dataset, with a uniform sampling to generate embedding matrix. They got an accuracy of 78.5%, as we can see from the first row. And when they tried different encoding, they got better results. Tubulate embedding, using the central frame approach, basically outperforms the more often used filter inflation method, and it gives an accuracy of 79.2%, as it has been highlighted. Next is deciding which variant is best. So on Kinetics 400 dataset, the unfactorized model, which is the model 1, that is a spatiotemporal attention model, it performed the best, but it overfits on smaller datasets like the EK. Now there is one more average pool baseline model, which you can see at the last, that they have used with model 2 backbone, which means that they are not using any temporal transformer, but output from the spatial transformer and then averaging them and predicting the classes. From the table, we can see that the accuracy for the average pool baseline model drops, which means it basically needs better architecture to model on the EK dataset as well as the K400 dataset. Further, from the table, we can also see that how floating point operations, params, and runtime is affected with respect to every model. From that, we observe that the unfactorized model required high computation and hence uses more flops, which is 455.2, whereas for the factorized models, since attention is calculated independently over spatial and temporal dimensions, that is, not every pixel interacts with every other pixel, they interact indirectly. Hence, they use like less flops. Model 4 adds no additional parameters to the unfactorized model 1 and hence uses the less compute. And the temporal transformer encoder in model 2 operates only on NT tokens, which is why there is barely a change in compute and runtime in the average pooling baseline, even though it improves the accuracy substantially, as we can see in the runtime of model 2. So this was all about Ablation Study. Next is comparison to the state-of-the-art models. For this, we considered 2 variants presented in this paper. for comparing to the state-of-the-art models, which is ViViT Large, FE, which is a factorized encoder, and another one is ViViT Huge. Nitin will continue on the further slides and will explain this in detail.
Now, as we can see,
sorry, I cannot hear anything. So are you talking?
am I audible now?
No, yeah, no, we can hear you.
Okay. I'll start again. In this, we'll see the comparison of the two ViViT variants to the different state-of-the-art models on Kinetics 400 dataset. The first line shows the metrics that have been used. So I'll explain the metrics briefly. Firstly, the top one. So for a prediction, if we get the ground truth as the class having highest probability, then we consider that as a correct prediction. Next, top 5. If we get the ground truth in the top 5 class having highest probability, then we consider that as a correct prediction. And the term views, I'll explain using an example of model X3D XS3. It has 10 cross 3 views, which says that it has 10 temporal crops and 3 spatial crops. T-flops, as we know, denotes trillion floating point operations per second. So these are all the metrics that have been used. As we see from the table, ViViT Large, here we can see, which has an accuracy of 92.7%, which underperforms the best 3D convolution neural network, which is X3D XS3. You can see here. Which has an accuracy of 94.6%. Then came the ViViT Large, which outperformed Timeless Former, having 1 cross 3 view. You can see here, this one and this. Finally, in order to increase the accuracies, we trained these networks on a large pre-trained data set, JFT. And we can see that the ViViT Huge outperforms all the other state-of-the-art models. You can see here. Now coming to the Kinetics 600 dataset, the best variant among the 3D convolution network is the X3D XL. It has been outperformed by the Timeless Former Large. As you can see, the accuracy 95.6. Next, we see that these current state of models have been outperformed by ViViT factorized encoder by a little margin of 0.7% here on top 1, but still lagged behind in top 5. Finally, the authors were able to leverage the use of pre-trained image weights from JFT, where they were able to spike the state-of-the-art accuracy by a margin of 2.9 here, which was best given by ViViT Huge models. So to conclude, ViViT is successful in implementing regularization and factorization at different levels to produce state-of-the-art models for video tasks. This model presents a unique way of factorizing spatial and temporal dimensions, which increase efficiency and scalability. In future work, we can clearly state that the removal of the dependency on image pre-trained models is an area for clear future improvements. And for the next step, going beyond video classification towards more complex tasks should be the aim. Thank you. Any questions?
So yeah, so I don't have too much question actually for this presentation. I think it covers most everything. So the only thing is I didn't see any implementation by yourself, because this paper it's proposed our architecture and there is not too much theory behind that. So it's really hard to say why it performs better. So if you guys could implement it with some state of art and give some comparison, maybe not on the large data set, but on the small data set, and to confirm the result proposed by the author in the experiment, that would be best. Okay. Yeah, sure. Who would be like the next one?
I'll go next.
Yeah, sure.
Share my screen.
Okay.
Okay. Can you see my slides?
Yes.
Okay. All right. So I'll go ahead and get started. Before I start, I want to say if you have any questions, feel free to interrupt me during the presentation. It doesn't bother me. And I do apologize, I don't have a webcam, so I have to do without that.
Okay.
But the paper I'll be presenting today is a proposal for an adversarial attack method called Towards Transferable Targeted Attack. The goal of the paper is to design an algorithm that generates adversarial examples to help evaluate and improve the robustness of deep neural networks. In order to accomplish this goal effectively, the new attack method is aimed at improving the transferability and targetedness of adversarial examples. The transferability is the ability of the algorithm to generate a successful attack on a network it did not train for, based on a similar or related prior training. Targetedness refers to the ability of the attack to cause adversarial examples to be misclassified as a specific target class, rather than any class that is not the original. So the paper points out two main issues with existing methods for generating these adversarial examples. One is that they suffer from noise curing, which is the process of iterative perturbations following the pattern of the previous perturbation, resulting in more noticeable changes over the iterations. And the second is that the adversarial examples generated by existing methods are either far from the true class or close to the target class, but not both. So this paper makes two key contributions to create a better adversarial example. The first is to introduce a loss metric, which uses the Poincare space to address noise curing. And the second is to encourage classification closer to the target class using a triplet loss. Here I'm going to explain a couple concepts that appear in the formulation of the attack method. So a logit is a simple formula. It's the inverse of the sigmoid function. It essentially takes values over the range of 0 to 1 and exaggerates them over the entire range of real numbers. Norms quantify the magnitude of a vector, and they're often used to normalize things. The three types in this paper you can see visualized here. The L1 and L2 norm are what most of you probably know as Manhattan distance and Euclidean distance. So the Poincare ball is an example of non-Euclidean geometry. In the middle of this figure B, you can see the Euclidean length of each of these line segments drawn is the same. And so you can see that as you get towards the surface of the ball, the Poincare distance tends towards infinity. The important takeaway here is, like I said, as you get closer to the surface of the ball, the distances tend towards infinity. These are the hyperparameters that the users can set to fine-tune the algorithm. Probably the most important one here is epsilon, which is the maximum perturbation of each pixel, which is limited such that the output images are not perceivably different from the inputs. All right, so I'm going to get into the existing methods for generating adversarial examples. Okay, so this equation maintains that the perturbations made in the algorithm are imperceptible to humans. So this is what I was describing earlier, and they set this epsilon value to 16. So, okay, the first existing method is the fast gradient sine method. It generates adversarial examples by generating noise in the direction of the gradient of the cost function. The effect that this has is it maximizes error between the image and the true label and does not target any specific class. So this version of FGSM is targeted, with noise instead aimed to decrease the cross entropy loss between the image and the target label. This makes the attack aim to produce a specific misclassification rather than any classification that is not the original class. Because in a black box attack, the gradient of the classifier is inaccessible, the momentum iterative fast gradient sign method is proposed. This version of FGSM improves the transferability of adversarial examples and creates a smoother noise output compared to other FGSM methods. The smoother noise output makes the noise less perceptible to humans. So now that we've seen some existing methods for producing adversarial examples, what are their pitfalls and what can be improved? The first issue is the vanishing gradient problem, which is the process of the gradient tending towards zero as iterations go on. This equation here shows this. As the prediction probability gets closer to the target label, the gradient decreases monotonically. And this is one of the factors that leads to noise curing. So in the figure, you can see that the Poincare metric is substantially better at avoiding the vanishing gradient problem than cross entropy. It doesn't decrease a whole lot as iterations go on. So here's a more visual example of noise curing. On the top row, each successive picture viewed left to right has the same noise layer applied, with the leftmost being the original image and the rightmost having the same noise layer applied 3 times. The bottom row is similar, except that each additional noise layer applied is different than the previous one. So although the changes made to the rightmost pictures are of the same magnitude as each other with respect to the original, the top image suffers from noise curing, making the changes much more noticeable. This figure measures the effects of noise curing. The top 2 lines here compare the cosine similarities between successive perturbations made with both methods, with the lower cosine similarity achieved by the Poincare attack method being desirable to avoid noise curing. At the same time, the Poincare attack method achieves higher target label probability than momentum iterative FGSM. This figure demonstrates the improved transferability achieved when adding triplet loss to the attack method. In green, you can see adversarial examples. Without the triplet loss, the adversarial examples are close to the true class marked in magenta. The addition of the triplet loss doesn't change the distance from the adversarial examples to the target class in blue, but they become farther from the true class. The result is that the attack produces adversarial examples that are more transferable, meaning they will be more effective in black box attacks where neural network architecture is not known. To aid in understanding of the design decisions of the attack, I'll walk through the algorithm for generating the adversarial examples. So a few important initialization steps are taken. The step size is initialized to the maximum pixel perturbation divided by total iterations. So all the perturbations are equally split between each iteration. Momentum is initialized to escape poor local maxima, and the adversarial example is initialized to the unmodified clean image. And this iterative process is done for 20 iterations. So the augmented image in the beginning is just a clean image, is input into each of 5 classifiers in an ensemble, and the output probability for the target class is used to calculate a logit for each classifier. These logits are later used to measure the distance from the target class to the model's prediction. Here we fuse the logits, which is just an arithmetic mean. And this is the most important step of the algorithm, which is calculating loss. So here I'm going to go a little more in depth because this is this paper's key contribution. So these 2 equations define the Poincare distance to be used in the eventual loss function. The distance is measured between U, the fused logits from the previous step, and V, the one-hot encoded target label. The primary motivation to use Poincare distance instead of softmax cross entropy is its ability to preserve the magnitude of the gradient in an iterative attack. This behavior is possible due to 2 properties of the Poincare distance. One is that the magnitude of the gradient only grows if the data point gets closer to the target label. And 2 is the target label is near the surface of the Poincare ball. So as the adversarial example gets closer to the target label over iterations, the magnitude of the gradient would normally tend towards 0 using softmax cross entropy. Instead, the Poincare distance's exponential growth as the example gets closer to the target class causes an increase in the magnitude of the gradient. The resulting behavior is that instead of each iteration becoming less and less effective than the last, momentum is preserved and an improved final result is achieved. So this equation here is the same Poincare distance. It's just a bit more of an explanation of how U and V are found. But as I said, U is the fused logits, V are the one unencoded target labels. This is the triplet loss equation used as the second component of the final loss function. It takes the distance to the target label and subtracts the distance to the true label, plus a hyperparameter gamma that defines a margin between these distances. This is the key to the improved transferability of the attack, since this incentivizes that the adversarial example be close to the target and far from the true label at the same time. So this is the final resulting loss function. It's just a combination of the Poincare distance loss and the triplet loss with the weight lambda applied to it. So this captures both the key contributions of the paper. The attack suffers less noise curing because of the Poincare loss, and transferability is improved with the triplet loss. Next step, we just calculate the gradient of the loss function. And using the gradient from the last step, we update the momentum. And then to update the image, the perturbation is made in the direction of the momentum times the step size alpha. And that's the end of the iterative part of the algorithm. So after all 20 iterations, the adversarial example is complete. So let's look at some results, see if the numbers prove the theory. So this table shows the success rates of each attack on each of the ensemble members and then the average on the end. It includes two models, the ensemble network, which is a white box setting, and the holdout network, which is a black box setting. In all instances, the Poincare and triplet loss attacks outperformed both FGSM-based attacks. This table shows similar information as the last, except that the models in this table are adversarially trained networks. Although the success rates are a lot lower in the black box setting, as you can see, the Poincare attacks still outperform both of the state-of-the-art FGSM-based methods. And this figure showcases some sample adversarial examples created by the Poincare attack. The top row are the adversarial examples, the middle are the clean images, and the bottom are the noise added to each clean image to produce the adversarial examples. And that's it. That's the end of my presentation. If you have any questions, feel free to ask.
Yeah, so I think like you already sent me your Medium report, right?
Yeah. Mm-hmm.
Yeah, see, like in the report, I also give you some comments. If you see that, like I would like you to explain more of this, what do you call the distance?
Yeah, the Poincare distance.
Poincare distance, yeah. So for that one, I think that it's still not clear to me why this can really help. So I would like you still to go more detail about that distance and why it really helps the case.
Okay, I already replied to your comments.
Okay, but I didn't read that. I will look at that later. So that is only my concern. So overall, after I read your whole draft, it looks very good, very nice to me. So only this part is not very clear. Okay.
Okay. If you have the time, I can try to explain it to you now. It's kind of difficult to do.
Yeah, so now it's not easy. So like I will read. So if I understand that, it's okay. If not, I will send you another message so you can reply later. Okay.
All right.
Yeah. So like I have a faculty meeting and I have to go. So there I see like we still have one or two like presentation for today. So I can give you two options. One is you can like still stay in this meeting room and you can present, and later on I can watch the video record, or you can present to me like a one-on-one, like we can also record that and then upload that to YouTube video like anytime today after 10:30. So from 10:30 until the end of day, so anytime works. So like who is still there? Who would like to present?
We'll be presenting our paper, so we are left.
Yeah.
But
So
how
would you
can we
like?
get how can we get some comments if we present right now in the recording?
I will. Yeah, I will watch that later and send you the message. So that is one way, and or you can just present to me after 10:30 a.m. so we can like personally.
Yeah. The issue is that my presentation mate has a flight to catch, so he is going home. So he has to leave like at 10:30. So can we do it right now, or
Yeah,
then we
yeah,
can...
yeah. If you want, you can just do it now. But I will leave, and later
Okay.
on I will watch that. Who
Okay.
else would like to present today, except for Apan? No others. Okay. Yeah. So I will just leave now, and you can just record. Okay. You can just present.
Yeah. Can you just make me like give me the permission to share my slides with others? And...
I think I already gave you the permission.
Okay.
You can share now, right? Okay. Okay. Good. Thank you.
Okay. Okay.
Mhm.
Thank you.
Mhm.